Hello, in this video, I'm going to talk about locomotion, which is also referred to as gait. So it is widely accepted that we have central pattern generators or CPGs. These are spinal cord mechanisms that offers a level of spinal control over our locomotion. So it's a mechanism in the spinal cord that provides the basis for stereotypical locomotive patterns, meaning gait, so like walking, running, skipping, jumping. So these are formed by networks of motor neurons that functionally work together in the spinal cord to generate the rhythm and shapes the pattern of locomotion. So it's an important control mechanism in locomotion, but it doesn't act by itself. So if we were just using CPGs with no sensory feedback, we'd get the movement, we'd get the limb movement in the normal locomotive patterns, but there would be very little coordination and control. So we would not have nice, clean, controlled, smooth movement patterns. We would trip a lot, it'd be really erratic, and we need proprioceptive feedback coming back from the limbs so that we can adjust and smooth and coordinate our movement. So CPGs generate those basic locomotive patterns right from the spinal cord, but the sensory feedback is really important for smoothing and controlling the overall movement. So the rhythmic structure of locomotion, there are distinct rhythmic relationships between limbs during gait, which are related to walking speed. So depending on the speed of gait, whether walking or running, we have different rhythmic relationships that take place between the limbs during normal stereotypical gait. And so it's really helpful to understand those rhythms and be able to observe and analyze them, especially if we're in any kind of rehabilitation type of setting, because then you can see anything that is abnormal. And you can also use it to assess progress and whether a program is working to improve those rhythmic relationships. So there's relationships between the limbs and there's relationship between the pelvis and the thorax. So all of which we can study and analyze to see if the person that we're working with is moving in the normal stereotypical way, or if there's something abnormal taking place that we can address through different interventions. Head stability and locomotion. So we prioritize head stability while we're walking or running. That's because think about all of the sensory organs that are on the head or in the head. The more we can keep the head stable while we are walking or running, the more accurate that sensory feedback is going to be. So think about like the vestibular apparatus and your equilibrium, your vision, and your ability to maintain focus on images that are in front of us, so that we're not tripping or whatever it is. So less head movement is better in terms of getting our sensory feedback and sending it back to the brain in an accurate way. So keeping the head stable optimizes vision. That's especially important for actions where we're running to catch a ball or some kind of object. So like it's one thing if you just need your vision to run, but imagine you're trying to run and track a moving object and be able to position your hands correctly to catch the ball or whatever it is. So vision and maintaining stable vision is especially important. The least amount of head movement in the vertical, so the up and down and the anterior posterior directions, occurs at a preferred walking speed. So the more we try to restrain head movement, the worse we are at it, really, and the more inefficient we are. But we naturally restrain our head movement at our self-selected preferred walking and running speeds. So it's when we try to make somebody walk or run faster or slower than their self-selected pace that we see less efficiency and less ability to keep the head stable. Gait transition. So here we're talking about the spontaneous change between walking and running gait in either direction based on speed. So where this gait transition happens, so at what speed this happens, is very different from one individual to another. There are many different individual factors between people that underlie when we go through those transitions. Within an individual, walk to run usually occurs at higher speeds than the run to walk transition. So basically, we tend to walk longer, even as speed is increasing. We stay at a walk longer and transition to a run at a higher speed compared to going in the opposite direction. We'll transition from run to walk at a higher speed as opposed to lower. So basically, we tend to walk more than run at the different speeds. So the best hypothesis for why we make these transitions is to minimize metabolic energy consumption, or VO2. So like if you try to stop someone from transitioning from walk to run, like you tell them you need to continue to walk, meaning there's always one foot on the ground at a time. There's no phase where both feet are off the ground, because that would make it a running gait. So one foot must always be on the ground at all times. You need to maintain a walking gait. So even as their speed is increasing, if you tell them that, then they're going to become less and less efficient compared to if they were able to break into a jog and start running. So walking really fast when you would prefer to be running is less efficient and is going to use up more energy than if you did just run at that same speed. Okay, contacting objects during locomotion. So sometimes we need to make contact with an object or target with our feet. So I'm not talking here about, contacting like catching a ball with your hands, but sometimes during locomotion, we are aiming with our feet to make contact with some target. So like maybe you're walking outside and there are puddles in the street or on the sidewalk, and you're aiming for the dry spots to miss the puddles. Or like in baseball, where you got to make contact with every base as you go around. Or like in our picture here, a gymnast contacting the springboard when performing the vault. So like really landing in the right location with the right amount of force. So sometimes we need to make accurate contact during locomotion. So it's very similar to an aiming task that requires movement by a certain distance to aim at a target. We use visual information to adjust our stride length based on tau, so our estimated time to contact. Now, interestingly, how most of us, or how we all strategize this from a motor control perspective, is that there's an initial accelerative phase. So we have stereotypic stride patterns. Like let's say a gymnast is running up to jump on the springboard and then jump up onto the vault. So as they approach the springboard, they're going to have the initial accelerative phase where they're running pretty fast and going in a normal stereotypic pattern. But as they approach and get closer to the springboard, they have to modify stride patterns to make up for the accumulated error from the previous phase. So like in the initial accelerative phase, you're not going to have exactly the same stride length. It's not going to be perfect. There'll be tiny errors on each stride. And when you add those all up, that could be, half a stride's difference, or it could be significant. And so in the zeroing in phase, that's where you get close to where your target is. And that's where you might have like stutter steps or, half strides, or sometimes awkward things happen in that phase. But generally speaking, you're modifying your stride pattern based on tau, based on your time to contact, so that you can be accurate in those last couple strides and be able to reach your target. And then the opposite, avoiding contact with objects during locomotion. So vision, of course, is critical. It provides information about objects that we want to avoid. So that could be like in our picture, jumping over hurdles, we want to avoid contact. Or it could be like if you want to walk through a doorway and avoid bumping into the doorway. And so our vision also provides body scaled information about the size of your body, or the part of the body that needs to miss making contact with the object. And so we might orient the body differently. So like, let's say it's a small doorway, you might turn sideways or you might duck down. So we'll orient the body in whatever way we need to fit through the space based on visual information. Vision also provides predictive information about objects that we need to step over. So visually, we are assessing height, width, shape, how solid or fragile we think the object is, and then we alter our movement patterns to step over that object. And depending on what we assess, we might give it more or less clearance. So like, for example, if we're stepping over something that we perceive to be fragile, we tend to give it more clearance. We tend to raise the toe a little bit higher to get over it because we perceive the target as fragile. Rather than if we perceived it as solid and not very fragile, we wouldn't feel the need to give it quite as much clearance because maybe it would be okay if we were less accurate and bumped into it. All right. Thank you so much for watching. Have a great day.